So in this video, we're going to talk about the center of gravity, which is often abbreviated as CG. And the center of gravity is the point where an object's weight is evenly distributed in all directions. And a low center of gravity, or a low CG, increases the stability, making objects less likely to tip. And therefore, an object is balanced if its center of gravity stays within its base of support. So we can break this down and visualize this with the help of these two illustrations. And we can start with the illustration on the left. So here we have an asymmetric rock which is being held by two chains. But if we take a look at the rock, we can see again that it is highly asymmetric. So we have this point O, which represents the center of the rock, or at least the center of the horizontal, of the length. But where is the center of gravity? Well, it's indicated by this point C, which is to the right of the center. But if the center of gravity is indeed the center, then how can this be? Well, if we look at the rock into two halves, we can see that this right half is actually where most of the mass of the rock lies. So therefore, the center, in terms of the mass, and therefore the weight, and the center of gravity will be shifted to the right. Now we can visualize this in a different manner using these force arrows. So we have the weight of the rock weighing downwards, and we see the contribution to the weight is larger on the right-hand side than it is on the left-hand side. Now with this right illustration, we can look at a different scenario. In this case, we have these rolling objects where a portion has been removed. So if we were to estimate the center of gravity of each object, for the left object, it would lie somewhere around here. And for the right object, it would lie somewhere around here. So therefore, which is the more stable configuration? Well, it's this right object, because it has a lower center of gravity. And again, a lower center of gravity increases stability, making objects less likely to tip. So that means this left object is likely to continue rolling until that center of gravity is at the lowest point, which is what we see here in this rightmost image. So now let's talk about the effects of imbalance and what goes on when the center of gravity starts to move away from the base of support. So again, when the center of gravity does indeed move outside the base of support, this is when it can tip and fall. And when this happens, a moment is produced. So counter moments, these are moments that counter that initial moment, which are in the form of forces or weights, restore stability by shifting the center of gravity back into the base of support. So we can look at this example of somebody trying to balance on a thin rope or a thin beam as an example. In the right illustration, we can see that the person's center of gravity is more or less directly above the beam, directly above where they're walking on. So there's no moment produced, and therefore no counter moment needs to be produced in order to restore the stability. But in this left example, we can see that the person's center of gravity is actually at some distance offset of the beam, away from the beam. So in this case, there will indeed be a moment produced that risks tipping and falling. So what this person can do is essentially shift their center of gravity by producing a counter moment, which again is some sort of force, or in some cases, an additional weight. And this counter moment can restore the stability, bringing the person back to something closer to what we see in this right image. But not all structures have this luxury. For example, if we're looking at cranes or tall buildings, it's not so dynamic or quick to respond. So in this case, it's very important that these structures are designed with a correct or appropriate center of gravity to ensure stability. And they do that by using counterweights, which can help lower the center of gravity, or likewise can use wide bases, which essentially play the same role. You're not actually adjusting the center of gravity directly through changing the weight distribution, but you're instead widening the base, you're increasing the area or the base of support, which also helps to improve stability. So let's talk about a few more real-life examples of how the center of gravity can play an important role. So again, it's important in many different structures. We mentioned tall buildings and cranes, but also in many applications. So it's not necessarily just going to be for an object. So first example we have here is vehicle design, where motor vehicles with a lower center of gravity are less likely to flip. So this can play a huge role in vehicle design. For example, if you're designing a race car, it's important that it has a very low center of gravity because they are going to be moving very fast and taking very sharp turns quite regularly. So you wouldn't want to have a high center of gravity on such a vehicle. The second example we covered already a little bit, which is structural integrity. Again, many tall buildings, towers, cranes like we talked about, remain upright thanks to wide bases or carefully placed counterweights. They're attempting to design or engineer the center of gravity at a particular position in order to ensure that it won't risk tipping or flipping. And a final common example that we have is that of athletic performance, where athletes can adjust their center of gravity for balance or another form of performance. So one example is that of a javelin thrower. So here we have the javelin thrower holding the javelin in the middle. So this is what's considered ideal from the perspective of a javelin thrower because this is the center of gravity of the javelin. If they were to grab a little higher up on the javelin or a little lower down on the javelin, well then it would be off balance and a moment would be produced that would require the athlete to produce a counter moment, which is essentially taking effort and energy away from throwing to the best of their ability. Now, another athletic example is that of a weightlifter. If you're going to do a shoulder press exercise or some very heavy exercise, you want to make sure that you have careful control over the center of gravity. In what we call here person B's case, their center of gravity is in the center of the weight. So again, no moment is produced, so no counter moment needs to be produced, leaving them to exert all of their effort towards accomplishing the task. But in person A's case, because they're holding it in an asymmetrical fashion, well then that center of gravity is not center with them. So this means a moment will indeed be produced, requiring a counter moment to keep it in balance, which will make this person's life a lot more difficult. So now again, let's summarize some of the most important points from this lesson. First of all, the center of gravity, often called the CG, is the point where an object's weight is evenly distributed in all directions. A low center of gravity increases the stability, making objects less likely to flip, and an object is considered balanced if its center of gravity stays within its base of support. When the center of gravity moves outside of the base of support, this is when an object can tip and fall, making it unstable. So when this happens, a moment will be produced that requires a counter moment in the form of forces or weights that is used to restore stability by shifting the center of gravity back into the base of support. And center of gravity is, of course, important to numerous structures and applications, with a few that we mentioned including vehicle design, the structural integrity of buildings, and lastly, the performance of athletes in many different scenarios.